So if you have a mixture of strong acids, basically what you're going to have is you're basically going to add, and this could be a mixture of strong bases, you kind of do it but the same way. What you really want to know is, in the end, both of these acids are going to have complete ionization. So you want to find out what the pH is or the final concentration of the hydrogen ions when you mix two strong acids. Really all you want to do is figure out how many millimoles you have and put it over the total milliliters and just add it up, right? So if you take your 20 milliliters of HNO3 and multiply it by 0.250, you get 1/4 of 20, which is basically you have 5 millimoles of hydronium from the first acid, that's the HNO3, a strong acid that completely ionizes. So we assume that for every 1 mole of this, we get 1 mole of that. Okay, and that we can only do because the equilibrium is far to the right because the Ka is a large value. So again, I'm referring back to the Ka, and if I was explaining stuff, I would really have to do that. That's a 5, by the way. And for the other one, it's 30 times 0.5, which is just 15. So we have 15 millimoles of H pluses from this acid, and we can literally just add that up, right? So we have 20 millimoles of hydroniums provided by the acid. Now, in the end, we need to get the concentration of hydroniums, it's just millimoles over milliliters, because again, the millis cancel if you're still not catching that, which gives us a concentration of 0.40 molar. That's our hydronium concentration. And again, of course, we can negative log that value, right? Negative log 0.40, and that gives us a pH of 0.39. And again, if that's our pH, we can always find the pOH by subtracting it from 14. So our pOH is going to be 13.6, because 13.6 plus 0.39 is about 14. And the hydroxide concentration in that solution is going to be 10 to the negative 13.6. And our calculator will spit out a more scientific-y, notation-y type of answer.